Okay, folks, so let's get started here. We were talking about stars now. We've transitioned away from planetary science, the best science of all sciences. And now we have to talk about the rest of the class. Oh, boring. So we were talking about the life cycle of a star. And we're talking about how we represent all of these different stars in many different ways. And I kind of brushed over this idea of how do stars get their energy. If you want, we can like dig into that idea of like how you power a star, or we can just like keep going through and like maybe get back to that later. So do people want to know more about what goes on in the inside of stars, or do you want to know more about the life cycle of stars? Mitochondria or the process of aging?
What do you think?
Life cycle.
What do you think is cooler?
I think they're both cool. Life cycle. They're literally both cool. That's why I made life cycle. Life cycle. Raise your hand for life cycle. Raise your hand for mitochondria of the star. Oh, okay. People like mitochondria of the star. Okay. Sorry. You've been voted down. Let's really briefly talk about the life cycle and what the HR diagram tells us, okay? Just so that we wake our brains up. We'll probably get a little bit of this in here. Okay, get the brain working. Okay. So what are the things we see in a star? What are the properties we can observe as scientists? Color, very good. And color tells us temperature. Good, done. What else can I tell? Size. How do I tell size? That's not something I can directly measure because I can never see multiple pixels on a star, right? That's an inferred property, but you're absolutely right that we do get size, intensity or brightness, right? And that tells us how far away something is, right? So for example, if I know that it's a certain type of star, I know how much light it's supposed to give off, and then I see how much light it is giving off, right? So I can tell how far away it is. That's an inferred property. And the third one, of course, being, what is its true brightness? Right? That's one that we have calculated in the ways that I'm about to show you. Anyone come up with a better acronym for this? Anyone even think about this one? They left the room? No, not even. Okay, good. At least we're honest. O, B, A, fine. Gelatin. Cool man. Okay. I don't know. We're gonna work on it. We're workshopping it. Okay. So what was this called again? Main sequence, right? And we'll notice that these lines in this direction represent solar radius, and that this is not parallel to these lines, right? These, in fact, get larger by a full 2 orders of magnitude. So this line here is 100 times smaller than this line here. And that's about the range that you see. Biggest stars are only about 100 times larger than the smallest stars on the main sequence. That's obviously not true when you leave, right? You can get up much higher on this one. What was it called when they're up here? Supergiants, or just giants is good. And giants would be fine, but supergiants is absolutely correct. Supergiants is even higher. Okay, and then you go down here and you're white dwarf. Okay, so that's the life cycle. And we'll talk about this in much more detail on Monday. But today, upon popular request, we're going to learn about how stars hot. Why star inside hot? Okay? Okay. And we're going to start with this idea. Right? Okay. You know that one? Okay. So they don't want to be next to each other. These are what? Not tennis balls. Don't say that. So, they are not suns, they are hydrogens. And they have a charge of one what? 1 plus. The pluses do not want to be together. Are there electrons in the center of the sun? One. No, they fuck off. Okay? It's really hot. They're really small. And if we just think about the idea of hot stuff, if we just think about the idea of heavy stuff sink, a proton is much, much heavier than an electron. And they've completely fucked off. Okay? So mostly what you're going to have is proton. Proton soup. Okay? And as I stick these close to one another, they're going to do something very magical. Right? What are they going to do? Fuse. They're gonna say, I am your best man. And one of them, in order to do that, will become. The whole thing becomes deuterium, that's correct. But one of them does a special thing.
It depends on.
Well, which one? This is a proton, this is a. The proton neutron together is deuterium. Okay. And then. It goes like that. What's that? What's that?
Another proton.
This is not yet helium. Why is this not yet helium? This is a neutron, and these are two protons. Stick them together. Stick this one with this one. I get tritium. I think I heard earlier. And I need two tritiums. Two tritiums, and I go.
It exploded.
And that never happens in a star. Okay, so here's my two tritiums, okay? Now my two tritiums, I go like that. I get that. And these two, they're done. Right, so what's this on my left hand? Helium. Because it's two neutrons and two protons. And these are still protons. I need different color balls. That would be a really great demonstration. Okay, so that's conceptually what's happening. And we're gonna play this game to build everything in the universe. Ready? You excited? Feel like you're not excited. Let's go build the world. Okay. Let's go. All right. So here's the what is that called? Table of elements? What is that? Periodic table. Okay. This is where you make it. These are the different colors. So hydrogen was made in the beginning. Helium is made over here in the beginning. Okay. And a very small fraction is currently being made in dying low mass stars and exploding massive stars. Okay. Most of the helium in the universe by weight was made in the Big Bang. But of course you say to me, wow, Matteo, you just said we're making helium. Stars are small compared to the weight of the whole universe. Okay. So that's okay. You're not freaking out about that? Okay. So this one here, these are our Big Bang babies. And you'll also see that lithium is also made during the Big Bang. Okay, but just a teeny bit of lithium, not anywhere close in weight. You'll notice there is no deuterium, there's no tritium on this. Those are isotopes of these same objects. So these are just different versions of H. They don't get their own rank. Okay. And we are made of what? Carbon. So carbon is mostly made in dying low mass stars and exploding massive stars. Cool. Nitrogen. Both of those. Oxygen only made in exploding massive stars. Huh. Okay. Cool. Love that. Let's say I have some nice jewelry on. Where is the gold here?
No, it's 79.
AU right here, right? Where's that made? Merging neutron stars. What? That's pretty cool. Okay. And let's say I'm really interested in blowing some stuff up. Okay. Also merging neutron stars. In fact, when you get down to about here, you'll notice there's a color difference, right? A lot of this is very purple. Whereas like the top was very yellow. Right? These ones here, we had to make at home. Here. Yeah, because otherwise you can't name it Einsteinium or Californium. And those are, you got to give stuff names, you know? So the funny thing, right, is that we knew that there would be a configuration that existed. We said, you could just stick some stuff together and it will fit. And the math was so correct that they predicted these and then they made them.
And then they're just continuously making them.
No. These are very unstable. These don't just hang around. Americanium. Come on, that's awesome. That's what I tried, but apparently they ran out of possible combinations. What? That's what the CM? Prismani Mateoum? I'll take where's CR? There already is a CR on here. Let's see it.
Chromium.
Yeah.
There it is. Chrismani, see, CRM. Wow, amazing. Okay, now we're having too much fun. Stop it. Okay. So in fact, here's what the distribution of abundance in the whole universe looks like. This is how many of every atom. Okay. So here's uranium down here. And over here is hydrogen. This is a log scale. So a difference here from 10 to 9 is a difference in a factor 10. So a difference from 11 to 9 is a factor 100. Difference from 11 to 2 is a billion. Okay. So the abundance of helium compared to the abundance of beryllium is very, very different. Okay. Here's boron. The fact that we had any boron on Earth would be pretty cool, actually. Right. What's that? Not that much, yeah. Cosmically speaking. And look at us, CNO. We're made of like, if you can't make us out of helium, because helium doesn't like to play chemistry, we're made of like the most abundant stuff. Hydrogen, carbon, nitrogen, and oxygen. That's like our main building blocks. Okay, HCN, ammonia, that's NH3. Those are the ices that we're finding. And we're finding them because they're the most abundant things in the universe.
Hydrogen, hydroxide.
H2S2, something like that, yeah. Okay, and then you'll notice something else that's weird, yeah.
So is that why, when they're trying to search for like life, they're always searching for hydrocarbons?
Yeah. So you're gonna look for stuff that puts H together with C's, right? Because we think hydrocarbons probably are the basis for life. Right? If you can't put those together, if they're separated, you're unlikely to be able to do anything else. According to the way that we understand life. You could have silicon-based life down here. That's been theorized. We just don't see any on Earth, so we don't think it's possible. Okay. What other thing do you notice here? So you see a general decrease. Anything else funny you see? A lot of groups. Yeah, what do you mean by groups?
Iron, cobalt, and they're all level. Some of the groups are kind of like level.
Like these ones?
To the right. Yeah.
Yeah, like that, right?
They're like bunnies.
Like bunnies?
Bunnies. Like
Buddies, yeah. Well, your nearby friends, you're talking about like that?